Okay, today I would like to introduce two really important applications using V2I communication in our modern intelligent transport system. So one is called the green light optimal speed advisory system. Another one is the vulnerable road users protection for buses. Both of these applications are developed for our project BDMove, which aims to create a kind of bi-directional, multimodal, connected traffic in Hamburg in order to improve the efficiency and safety of the public transport. Our IFAC developed both of these, the GLOSA for buses and the vulnerable road users protection system for a bus. In our daily life, we have noticed that there is a case that if a bus is leaving a bus stop and it's really hard for the bus driver to know how much time remaining for a green signal and at which speed is appropriate for the bus driver to drive the bus across the intersection without stopping. And also if the bus is going to have a turn while simultaneously the vulnerable road users like cyclists or pedestrians, they are going straight. So maybe it will cause a kind of clearing points here. So we can use some infrastructure like thermal cameras or radars to detect and catch the trajectories of the road users. And also we can use the data inside the intelligent traffic system. But there is a question. So how can we deliver this information to the bus driver and to inform them how fast should they drive? So here our IFAC developed a kind of onboard unit to be implemented on a bus to tell the some useful information to the bus driver and to communicate with all the infrastructures in the intelligent transport system. So here comes to the first part, the GLOSA for buses. Due to the traffic jams and emissions today, someone has already raised up a kind of GLOSA algorithm for the vehicles. For example, here it's normal that for a vehicle, it can meet right signal at an intersection, and the vehicle has to stop to wait for the next green signal. Then it will start and go through the intersection again. However, with the help of the GLOSA system, it can help the vehicle to go through the intersections without stopping. So similarly, in our case, we developed a kind of GLOSA for buses to help our public transport more comfortable for the passengers, and also we can in this way increase the punctuality according to the driving plan and to reduce the energy consumption caused by the unnecessary stopping at the intersections. This is the communication architecture of our intelligent transport system. So this is the onboard unit which is implemented on our bus. And this is the field device constructed by a traffic light controller connected with a roadside unit. And this traffic light controller will be connected with the traffic center to deliver the required data to the public transport strategy computer. And this strategy computer will decide which will be the next traffic plan, which will be the next signal for the intersection. So this is called the forecast spec messages. This is signal, phase, and timing messages. And this message will be also broadcasted by a roadside unit. So in this way, both the future and current map and spec messages will be received by this onboard unit. Then this data will be collected and processed for a further application like our GLOSA for buses. So for calculation of the desired speed for the bus goes through the intersections without stopping, we have to prepare these inputs like the bus routes, the current spec and the future spec messages, and also the map messages. So with these inputs, we will know the distance between the bus and the traffic light. And also we will know the time remaining for the next coming green signal. So with this input data, we can know the desired speed as the distance to intersection divided by the time remaining for a green signal minus the time to close doors. So it has to be noticed that for a green signal, we have two moments, the start moment and the end moment. So in this case, we will know that we will get a desired speed range rather than a fixed value. So after calculation, we will get finally these 6 cases. So the speed range between V1 to V2 is the required speed range to help bus drivers go through the intersections without stopping. However, in order to avoid extra stops and starts at the intersection, and also we have to avoid the buses run too fast or too slowly. So we have to set a permissible speed range between the minimum velocity and the maximum velocity. So our suggestion is to tell the bus driver, try to run the bus in this common range. So however, in this case, if the maximum required speed is still smaller than the minimum permissible velocity, then we will suggest the bus driver to wait at the bus stop and until the case B occurs. So similarly, for the last case, if the minimum required speed is still larger than the maximum permissible speed, then we will suggest the bus driver to wait at the bus stop until the case C occurs. For simulation and the validation of our GLOSA for buses, we have selected an intersection along the bus route 26 in Hamburg. And we set the minimum speed as the 5 meters per second, and the maximum speed is nearly 50 kilometers per hour. So we have successfully implemented our GLOSA system on a real bus, and this speed-move bus has already been exhibited at the ITS World Congress last year in Hamburg. And we can notice that there is a display with the same signal changes as the traffic signal. So here, this bar shows the remaining time for the next signal changing. Okay, after the simulation, we will get in total 20 groups of GLOSA buses and non-GLOSA buses. In this diagram, the blue bar represents the GLOSA buses, the red bar represents the non-GLOSA buses. And after calculation, we can know for the GLOSA buses, they need on average the 43 seconds to go through an intersection. While for the non-GLOSA buses, they need 54 average time to go through the intersection. And this diagram is the waiting time of buses at the intersection. So we can see here for our GLOSA buses, just at 2 cases, they only need to wait for 1 second. However, for the non-GLOSA buses, they have to wait longer at the intersection. So here for the non-GLOSA buses, they need in total 190 seconds to wait at the intersection. So obviously, it helps the buses save nearly 99% of the waiting time. As mentioned before, we have to consider the safety of driving. So we have to predict the vulnerable road users, where they would like to go and how fast they will go, and whether there could be clearance on road. Firstly, we have to implement such infrastructure like the radar or thermal cameras at the traffic signals to catch the trajectories of vulnerable road users. And also this data can be broadcasted by a roadside unit. This information will be received by this onboard unit and transferred to the driver, and they can inform the driver with different warning levels, such as a display on a monitor or LED. So the method we applied is the clustering-based quick bundles algorithm. For this occasion, we designed two different modes. For mode A, we sent warnings according to the distance to the clearing point. For mode B, we use the time to clearing to send warnings. So firstly, when the MQTT messages, including the geolocation and speed data of the road users to the onboard unit, then we use this clustering-based method to predict the vulnerable road user's trajectory. And after a noise reduction, we will calculate the distance and time to a possible clearing point. And then we will send warnings with different levels to the driver. So in fact, we have interviewed many bus drivers. What are their ideas about some warning systems, like a kind of vibrating seats? They can vibrate with different frequency to tell the bus drivers if there is something happen or not. So, most of the drivers, they don't like such device to send warnings because they feel it's annoying for their driving behavior. So in this case, we designed this triangle sign on the display to tell a dangerous case to the bus driver. And also we implement a warning LED in the right A pillar. For the algorithm validation, we selected these 4 intersections along the bus route 26 in Hamburg. And after a large amount of data collected by these thermal cameras, we start to make a simulation. So here is also the practical system implemented on a real bus. We can see how it works. So here, will someone come and it shows, and if he's leaving, it will disappear, and now it shows again the dangerous case. After simulation, for mode A, we get a result that it predicts 8% of the total cases as the clearance cases. However, for the mode B, it predicts 47% as a dangerous case. So if we improve the distance to send warnings, like here from group 1 to group 2, we increase the distance to send warnings from 15 meters to 35 meters to make the warning system more sensitive. Then we will increase the percentage of clearance cases. So it's really hard to say which mode is better or more accurate because we cannot make sure if a clearance doesn't happen, we can say is a correct prediction or not. So there is only a difference between the mode A and the B is the sensitivity of the system. So the bus driver can choose how sensitive they want the system to be. After evaluation, there is an interesting topic. So because we have got a large amount of data, so why not we use or consider the deep learning methods like the long short-term memory model to process the time series. And also we can use CNN to process the images obtained by the cameras. But because the limitation of our current intelligent traffic system, we have really a high demand to send warnings in just 1 or 2 seconds. So the current technology is not prepared for this high speed of calculation and prediction. So, but maybe in the future, I think if 5G or 6G, they can be well implemented in the traffic system, is a good direction to consider the deep learning methods. And so that's my presentation today. Any questions?